Okay, let's get rolling today. Let's see, in terms of announcements, we do have a test scheduled on the 19th. That'll be our pumping test on Learn and iLearn. I need to go back. I've got some stuff put together. I'm not sure how many questions. I'll give you an update as we get closer to it, but it'll take you the whole class time, I would expect. So you might, I think you probably should have PSAT available to you. So if you have any issues on the download, be sure and let me know. I know it's still out there because I've looked for it recently. I won't make you do measure. I think you know my opinion of that on pumps right now. It could use some improvement, but yeah, by and large, there may be some small problems. I don't know. I need to review it and let you know. But I mean, you need to go back through all the slides, and I'd look back over that reading document. There's a lot of good information in there. Okay, so last time I think we finished up with the reciprocating compressors. We did a little bit about predicting loads. If you have a load-unload scenario, you can calculate percent time on, percent time off, and use the maximum capacity of the machine to give you some sort of an estimate of how much air is being produced and consumed. So that's what that was about. So rotary screws. So you see in the center, that largest picture is of the screws. And basically what happened, and then you can see it in the housing. So air comes in and gets trapped in the area between those screws. And then as they turn, it's forced down the length of the rotor, and the cavity that the air is in, the volume of it gets smaller. I mean, I don't know who designs these things. I mean, I think it's pretty amazing. I would hate to have to been somebody to design this, but I mean, it turned out to have been a really good idea. And you know, all that's computerized, CNC controlled on the milling machines and all that stuff that cuts those things. But pretty interesting. And, you know, I think it's an area of constant research to try to make those things more efficient, make them do the compression with minimizing the amount of power that is required to do it. But, okay. And so we do have lube injected and lube free machines. We'll talk about the lube injected. And so there is a spray of oil that is sprayed into the air as it enters the screws on the lubricant injected machines. The lube-free machines obviously don't have that. And the rotors there are kind of like have a Teflon type coating on them to try to reduce the friction as much as possible. And we'll talk more about it. We've got slides on all this stuff as we go through. So the lubricant injected on the lubricated, well, all compressors have some lubricant in them, but the lubricant injected compressors are the ones that spray it into the air, the compressed air. And that lubricant actually fulfills three different operations. It does some cooling, it does lubrication, and it does sealing. So having that oil film in there on the surfaces helps keep the air from leaking outside that little cavity as it moves down axially. And then if it was leaking, the machine would lose capacity and it would lose the ability to generate higher pressures as well. And then as the air comes out with the lubricant in it, it's removed from the compressed air in the oil air separator, which has a sump down at the bottom, and the lubricant just kind of is separated out with a separator element and then falls down to the bottom and gets pumped back. It's pretty hot at that point, and it gets pumped back through a heat exchanger. Which is either air cooled or water cooled, and gets cooled down and then just gets pumped back in. So the lubricant just makes a little circuit inside the compressor. Like I said, compressors, they can be air cooled or water cooled, and we can recover some heat from these things, which I think we talked about that the first compressed air lecture a little bit. Lubricant free screw compressors, like I said, they have a Teflon type coating on it to try to reduce friction. Turns out they're not as efficient because that lubricant does a better job reducing friction and losses than the Teflon coating. Again, air water cooled. Heat rejected from the lubricant free compressor is typically at a higher temperature given the same operating conditions and ambient conditions, because that lubricant free compressor is not as efficient. It has more heat to reject, and so you typically will get higher temperatures. If you're doing heat recovery, maybe that's not so bad, but like I said, most people do not recover the thermal energy from the compressors. So that last bullet is good heat recovery potential because of the higher temperature of the heat that's rejected. That's kind of what a skid looks like. A lot of times they have this nice, pretty metal box around them. Has some thermal protection or not thermal, but acoustics in it to try to reduce the noise levels a little bit, because they can be fairly noisy. We've got some other diagrams where I'll go through some of the components. So this is the most common type of industrial air compressor that we see these days. I bought a little, I don't know what horsepower that little one is that we got over in the ISC office, but I mean, the whole thing's no bigger than that. And I thought I would have to buy a reciprocating one. I wanted to have a little compressor over there. And they had a screw machine. So they make them even smaller than, I know that's not 10 horse, that's maybe 2 horse or something. So they make them small these days. Largest, I have seen 1,000 horsepower. I've seen, I've recommended, Atlas Copco makes a 1,000 horsepower lubricant free machine. But typically about 500-600 horsepower is the biggest that you normally see out there in the field. And common sizes are 50, 100, 150, 200, 250, 350, something like that. Probably 100 to 200 horsepower is probably the most common, but it just depends on how much air a plant needs. We've talked about the operation. We got male and female rotors. The air gets trapped, volume gets reduced, and it usually spits it out the bottom. Lubricant injected. And operating cost, so there's our specific power, 18 to 19 kW per 100. So that's kind of like, the lower the number, obviously, the better it is, right? If it was 5 kW, wow, that would be super efficient. So the best number that I've probably ever seen in reality is probably a 14. Some big centrifugals can get down to maybe 14 if they're operating at full load. Because compressors, I don't know that I've said this, the most efficient operating point for most compressors is 100% load. It's using all max power and it's making max air. When you start backing off, they start losing efficiency and that kW per 100 goes up. The exception to that is the variable speed compressor, because it's meant to operate at less than full capacity. It's meant to be the trim machine that responds to changes in compressed air demand. So it's sitting there looking at the pressure in the system. When the pressure drops, then that VFD automatically ramps up a little bit to produce more air. And so it's ramping up and down. So the whole concept of the variable speed compressor is as the part load machine, the trim machine to respond to those changes in demand. So they are optimized to be more efficient in the, like, I don't know, 40 to 60 to 70% in the middle of the load range. But all the rest of the compressors are optimized at 100%. And so they tweak the screws, they tweak the design a little bit in order to have some particular operating range that is peak efficiency. Okay, that's a pretty good picture of what the screws look like. And in terms of a diagram, I've got a couple here. So we can look, inlet air comes in, and this doesn't show it, but there'll be a filter. There may be 2 stages of filtering. I'll tell you a story. A friend of mine that does a lot of work with compressed air, he was at a plant, and they had some big compressors, and one of them they could not hardly keep online. They couldn't keep it loaded. It kept going off. And they couldn't figure out what the heck was wrong with it. Oh, lovely. I have unstable internet. Let's hope it's back. So the compressor technicians came in and they checked everything, and they really couldn't find anything wrong with it. Well, it turns out that they had 2 inlet filters. There was an inlet filter right there at the compressor that got changed. And then there was an inlet filter, the air, there was a good sized duct bringing air into that. And nobody knew, but there was a filter up on the roof that they never changed. And so over the course of 5, 6, 7, 8, 9, 10 years, that thing got packed. And so the air compressor couldn't draw any air much into it. And they kept checking the filter down here, and they said, well, look, it's clean. It's a brand new filter. Well, finally, somebody went up on the roof. So let's go up on the roof and see what's up there. They went up there, and down behind some smokestack or something, they found, oh, this is the inlet. Look at that. I didn't know we had a filter here. And they looked at it, and it was just packed. And so this thing had been running, not producing much or coming offline. And that saved them like $100,000 a year, because this was a big machine, because they had to run additional compressors to make the air that this guy couldn't make. So anyway, stuff happens. But
How long until they realized there was a filter?
oh, it had been there for 5 to 10 years.
Not working, right?
Well, I mean, it just gradually deteriorated. You know, it finally got to the point that they called somebody in. I mean, they called the mechanics in, and the mechanics would go through the machine like Ingersoll Rand or whatever, and they would say, there's nothing wrong with this machine. And just nobody, and there's an inlet filter and the whole deal, and nobody ever thought, because, you know, I mean, it's a big plant, go way up on the roof and all that. Nobody went up there. And I mean, it was $100,000 for going up there and changing filters. But I mean, stuff happens out there all the time. I mean, you just shake your head. So anyway, we got our inlet air. Now, it's interesting, and we'll talk some more about this. It's like I may have shaky internet again. I don't know. The temperature of that air can have an impact on the efficiency of the machine. Colder air, because these machines are going to pull a certain, you know, if they're operating at full load, they're going to pull a given airflow volume of air into them. The question is, how much mass do you get with each volume of air? If it's cold outside, you get more mass, and so you get better performance out of the machine. Now, if it's a lubricant injected machine, you're spraying warm compressor lubricant into that air as it enters the machine. So that tends to mitigate this effect on a lube injected machine, but a lubricant free machine doesn't do that. And so if you're pulling air from outside, in the wintertime it gets cold air, in the summertime it gets hot air. Okay, if you're pulling it from inside the compressor room, it probably gets pretty warm air all the time. It depends on the plant, but these compressors put off some heat, and a lot of times air compressor rooms stay pretty warm. So that can be an efficiency issue on a lubricant-free machine. Not so much on a lubricant-injected machine. But it can also be an issue on a centrifugal machine or a reciprocating machine. Okay, so anyway, here's our air come in. This is our lube manifold. And so this is our injection, our spray line. So the air comes in, we spray into it. We also have some inlet bearing and shaft sealing, some lubrication there. There's some more bearing lubrication. But this is the spray of the air. Goes through the compressor. So then we have a lubricant and air come out together and go to the separator. And so then this separates, and it's 99.89%. It's 99 point, it's like ivory soap, man. It's pretty good. It's not perfect. We do get some lubricant carryover from these. And keeping that separator and that working properly is a big deal. I mean, if that starts not working or passing too much lubricant, you're going to wind up with all your lubricant out in the lines and oil and a big mess out there. So you gotta do your maintenance on that air lube separator. So the air goes out here, and it doesn't show the heat exchanger, but it goes through a heat exchanger here. And then we have a scavenger line that comes back, but most of the lubricant falls down to the bottom to a lube pump. It's got a lube cooler. It's got a bypass. So when you first start the machine up and the lubricant's cold, you don't cool it. You want to heat it up to the correct operating temperature so you can bypass. And then you filter it, and then it goes around in a circle. So the air just comes in, goes through the compressor here, and back out to the heat exchanger. That's one picture. Here's another picture. Of course, there's not any one picture that's going to be perfect for all compressors. But this is pretty similar. So here we see a two-stage inlet gas filter. Air probably. I mean, you can compress other gases. It doesn't have to be just air. But so it goes in, enters the screws. Here's my cool oil injection line, goes into the compressor where it gets sprayed in. The hot, oily air comes out, goes through this separator element. The oil falls down to the bottom. The air, with just about all the lubricant removed, goes through here, some filtration, and then goes into the heat exchanger. So this heat exchanger, it's got two functions. It's going to cool the air on this side, and then here's the exit pipe from the compressor. And then I've got the oil falling down to the bottom here, still hot, going over here, being cooled off, then being filtered, and then going back to the machine. So that should give you a pretty good idea of what these guys are doing. And then, of course, there's a control package on it. This is some data I pulled off. I think this is Ingersoll Rand data, but there's umpteen good compressor companies. Solaire is a good company. Atlas Copco is a good company. Gardner Denver is a good company. Ingersoll Rand. And I'm sure there's one or two more that I'm forgetting. But they all, I mean, they throw off against each other. You go in a plant that has all Atlas Copco, and all the people are, those Ingersoll Rands. We had one of those and it fell apart. You go another plant that has Ingersoll Rand, they say, those Atlas Copcos, they're not worth a flip, I mean, it's like automobiles. Some of them just have bad days. You got to fix them and go on. But anyway, I think this is Ingersoll Rand data just from a number of years ago. But just to have something. So, they make certain model numbers. For outside the states, the electricity is 50 hertz instead of 60. So, and if you're ever buying an air compressor, you want to get the hertz right. You don't want to buy a 50 hertz compressor for, Cookeville, Tennessee. It's not going to work very well. And then they have different rated pressures. You can get them much higher than this. These would be kind of standard. 125 is pretty standard. Some of them are 110, if you're sure you're not going to need to go up in pressure. And the higher the pressure is going to cost you a little more for the same. If it's high enough, it may have to be a two-stage machine where you compress it part way, cool it down, and compress it again. Some of that, which adds expense, adds efficiency. Here's the nominal horsepower of the motors. These are the flows. And I don't know if you remember, I said that, you need to remember a number in terms of air production for 100 horsepower. That's a standard number, because if you get a 300 horsepower, you just multiply by 3. If you get 1,000 horsepower, it's easy. Okay. So, if you think about this, my number is probably 450, 500 if you're in a hurry, because the math's easier. So for a 200 horsepower, if I was say 450 times 2 would be 900, and so plus half of that for the 50 horse. So you see that's someplace in the ballpark of 1250 CFM. So if you're going to be literate in compressed air, you have to be able to look at a horsepower and have some kind of a general idea how much air that thing should produce at full power. It's like, if you go in to buy a new Honda and the guy says, oh man, this thing makes 5 miles, it's 5 miles per gallon. And you don't have any number to compare to, you go, wow, that's really good. I want to buy 2 of those. And then you go to the Nissan guy, oh, ours is 35. I go, holy crap, what did I buy this thing for? Because you didn't have anything to compare to, So that's why we like to pick up some of these numbers as we go along. So, there's 400. So, 4 times 4 is 16. So, that 450 might be a little much on this one, but it's going to be, sometimes it's going to work, sometimes it's not. If it was 500, then it would be 2,000. And you see, a lot of times, what is it, Quincy? I think it's Quincy that rates their 100 horse machines, the low pressure at 500. Most of the manufacturers don't call out 500 CFM. I don't know if that's a real number or not. Most of them are between like 420 and 470, something like that. But I believe it's either Quincy or Solaire that they consistently call out 500. I've always wondered if it was real. I don't have any way to really know. And then if you do the calculations, I just did that one on the EP300, and it comes up 17.9 kW per 100 CFM. 18 to 19, someplace in that ballpark is what you expect to see. And that's a full load number. See, these numbers are full load numbers. When we start turning things down, efficiencies change all over the place, and that number is going to go up. It's not going to get better at part load, except maybe on a variable speed machine. Okay, so again, control types are critical to understanding air compressors and efficiencies and all that kind of stuff that we want to look into. So, start, stop, hey, it doesn't get any better than that. Put your control band in there, run it up to the high pressure, turn it off. Run it to the high pressure, let it coast down, turn it on, turn it off. But we talked about that before. Problem is you can't start and stop that big motor constantly. So now if you have a soft start or a VFD, then you could do that. But if you don't, then you can't do start, stop. Load, unload. So with load, unload, the motor runs continuously, but we somehow unload the compressor. So it's turning. We may restrict the amount of air. We don't let any air in. If you don't let any air in, you're not going to get any air out. And so it's sitting there spinning with the frictional losses and all that, but you just can't get any air. So it can't make anything. So it either runs fully loaded or zero loaded, but the motor runs the whole time. Modulation on the screw machines uses a butterfly valve, and I got a picture of it coming up here on the inlet. So at that inlet, you got your filter sitting up there, the air goes through the filter, and then there's a butterfly valve. That butterfly valve, you know, if it's like this, that butterfly valve can be wide open, in which case it doesn't obstruct the flow at all, and then it just starts, as you want less and less air, it cranks over to the point that it can close off completely, okay? So that's what the modulation is about. Auto dual, that's kind of a catch-all term. Some of these control modes will be maybe modulation from 50 to 100% and load unload from 0 to 50. So they combine and it automatically shifts from one control mode to the other based on how much air that it's producing. That's kind of what that means to me. Variable displacement, there's a couple ways to do this. It actually, it changes, well, in one technology, it changes the location. It has a slider valve, and it changes the location that the air is introduced to the screws. So basically, it makes those screws longer or shorter. Okay, and so if you use the entire screw length, you get full capacity, but if you slide that valve down, you get less capacity. You can still get the same pressure, which is a little bit of a conundrum, but it does work. And so that's called variable displacement. There's also Quincy does what they call a poppet valve. And so they have 4 little like piston-like valves. And they can, if you're at full load, they're all shut. And if you want to go down to reduce load 25%, you pop one of those valves open. And it basically takes that section of rotor out of the compression. If you want to unload it again, you pop another one. You pop another one, you pop another one. So they got 4 poppet valves. And they claim that's a better way to do it. So that's variable displacement. And then we have variable speed, which just, you know, with the variable frequency drive ramps the speed on the compressor up and down. Okay, so some diagrams. This is the suction throttling or the modulation, synonymous terms. So this would be wide open. So this little valve is pretty much straight up and down, discharge valve. We start modulating back, maybe we're 45 degrees, and then we're closed off all the way, okay? So this discharge valve is open, but there's nothing coming out because we're not letting anything in. That's the picture. That's a good picture. That's one of the better compressed air pictures I ever took. And you see, that's on an operating compressor. And these little supports over here, there was 3 or 4 of them. And the air filter set down. And, you know, those things held it in place. And then there was a little cap with some kind of a wing nut or something that went on top of it. And then the air would get pulled in the sides and filtered and then go down into the compressor. So you can see it's a little bit down over here and a little bit up on this side. If you could see, that flat valve plate is cracked up a little bit here and it's cracked down a little bit there. So I would say that compressor was running, you know, 10, 15, 20%, okay? So this little hole is here so that we can get a little bit of air into this even when it's unloaded. And you do that so that you can still pull some lubricant through the screws. That's not enough to produce any air to go out to the system, but it's enough to move some lubricant through so that you don't have lubrication issues when it's unloaded. So that's what that's for. Okay, so now there's quite a bit to know here about the load unload capacity. This would be the unloaded condition. So the unloaded condition, this valve is shut, and that little gap is because of that hole, to show that we got just a little bit coming through here. So let's say we've got a pressure band, 110 on the high side, 100 on the low side. So this guy's working away, producing full air, pressure goes up. And you can think about the controls, unless you have some master controller, you can think about a little man. I love this analogy. It's a little man that lives up here in this discharge pipe. And what's he got? He's got a pressure gauge, and in this case, for load unload, he's got one switch. And the switch says 100%, 0%. And that little man sits there his whole life and looks at that pressure gauge. He's got a high pressure setting, he's got a low pressure setting. So he's sitting there, let's say it's 100 on the high side, 110 on the high side and 100 on the low side. Little man sitting there with his hand on the switch. If that pressure is less than 110, that thing's in the 100% position. It's making all it can make. As soon as that thing hits 110, he turns it to the unload position. It makes no air, but the motor keeps running. He sits there and watches. 109, 108, 107, 106. It hits 100, 100%. He just sits there his whole life. Pretty boring, you know, not a job you want. Sits there clicking that thing. That's how load unload control works. You can adjust the high pressure, you can adjust the low pressure. Pretty much that's what you're going to get. Now, so let's say we hit 110. A little man clicks the compressor to 0 air, unload. So at that point, this air oil separator is at 110 pounds of pressure, right? Because he's sitting up here, this thing was 110. He clicks the thing, this thing is still at 110. We stop making air, we're still bleeding out into the system, but this is at 110. So now you can't, now the motor current is not going to fall to its lowest level until we get the pressure off of this sump, because we're pushing a little bit of air through this thing, and there's pressure that compressor's seeing with that little bit of air. And so that holds the motor amps up. So we got a bleed valve up here, but we can't just pop that valve. If we do, that lubricant in there will foam, make all kinds of bubbles and foam. And then the next time we load it, those bubbles and foam are still in there, it blows it out in the system. We spend a half a day operating like that. Where's all our compressor lubricant? It's out in the system, in the piping. So now different manufacturers have different timings on this thing, but the typical is about 40 seconds. And if you're standing next to one of these machines, you can hear it unload. It's, you hear kind of a clunk, and there's a drop-in sound and all that. And then you hear this, and I can't do that for 40 seconds. Assume that went on for 40 seconds, and then that pretty much dies out. Unless they've turned that off for some reason, or whatever, right? They can, controls people can do all kinds of things, but that's the general operating scenario, okay? And so the important thing to know, it's important to know this about a lube injected compressor. So if it's running load unload, it unloads, and I've got traces of the current will fall, and then it'll continue to trail off, trail off, trail off, trail off, until we get to the end of about 40 seconds, and then it hits a minimum value, and it sits there until the thing loads again, okay? And we have to do that to keep the lubricant in the machine. Well, there you go. You put a current logger on, and that's a 50 horsepower, so that's a pretty small compressor, and it's hard to see. This is 60 amps up here on top, 55, 50, 45, 40, 35. Okay, so now look what happened. So So this thing, it was trending down, pressure hit 100, little man hits a switch, current jumps up, and then compressor's running full loaded, amps going up because pressure's going up in the system. We get up here, the pressure hits 110, little man hits a switch. And look at, so you see we get almost an instantaneous fall, what was that, over 50% in amps, and then we see it trail off. Well, see, this trail off is the bleed off in pressure of the sump. This is a classic, trace on current. And then and see, if I had pressure on here too, you would see the pressure being at 100, and bingo, the thing loads. Now we're making full air. Same thing over again. And the length of the load unload is just determined by how much air is coming out of the system. This is a 50 horse, so I would expect this to be what, 225 CFM. So if this system was using 225 CFM, then it would never, the pressure would never go up. Because I'd be putting in 225, taking out 225, so it would just sit there. So obviously it's using less than that because the pressure goes up and it unloads and all that. That's caused by the lack of demand. Now, and we can check timing on this, but look at this cycle. This cycle is very interesting to me because look, it stayed unloaded longer and the current fell to 30 amps. Whereas in these cycles, the current didn't get below to about 36, 37 amps. Well, so what happened? Well, that's probably a break. Somebody that was taking air quit taking air. The demand went down, so the pressure didn't fall as fast. And so the sump got blown to a lower pressure. It looks like it got down almost to the minimum. Because see, this thing is starting to bottom out. It may be that was like 35 seconds, maybe another 5 seconds would have pulled it, would have come, flat, that sort of thing. But now, that's interesting to look at because think about the average current. So let's say this cycle starts, well, it loads here, let's say it starts here. So think about the average current draw from this point all the way down to this point and compare it to, say, this point all the way down to this point. So which one of those two cycles will have the lowest average current? Well, the one that comes all the way down, right? Because it spends time down here below 35, 30, all the way down here. So I could save energy if I could make all of the cycles look like this long one that falls down. How could I do that? Potentially. We'd have to run some numbers. I could add a big storage tank. I could add a big receiver tank. And so when this thing loaded, it would load longer because it would have to supply the system plus charge the storage tank. But when it unloaded, it would have a whole bunch of air stored at high pressure. And so then it would take a lot longer for the system pressure to bleed from 110 down to 100, and it would let that current come down and spend some time at that very minimum level. And so over the course of a day, a week, a year, I'm going to use less electricity. That's an interesting concept. So that's one of the things that we look at, and we'll get into some equations for calculating storage. But on load unload systems, we would show that we would call this short cycling. And if we check the timing on it, but I mean, you don't even really have to, you can just look at the cycles. And if you say, okay, this thing would come down and bottom out if it was unloaded for 40 seconds, 45 seconds, whatever the manufacturer said. Well, these first couple cycles, it's coming nowhere close to coming down and bottoming out. So that's probably an unload of, I don't know, 10, 15 seconds. So that thing is just, it unloads and the demand is such, and there's no storage in the system. So the pressure just falls down almost immediately and the compressor loads again. Well, that's wear and tear on the compressor, more maintenance, and it jacks up the energy use. Okay, so this is why we look at these current traces. You know, you log this thing for a week or two, a week, and come back and look at it, and you see all kinds of things. You look at what happens on Saturday and Sunday. What happens at 3 o'clock in the morning, you know, when production, maybe they're making something, but half the plant shut down. Do we have an opportunity? Could we turn a compressor off from 10 o'clock at night until 6 o'clock in the morning? Well, by looking at these current traces on all of the compressors and putting them together on one curve, you can come to understand what the system is doing. Okay, so, and I have multiple slides that pound home. So this is 100 horse, and see, this is probably a better picture. Now, in this case, we didn't add storage. They went on probably lunch break, but it's the same thing. You know, you see the pattern when the demand goes down, or if you added enough storage, you could make all of the cycles look more like that. Maybe not to that extent, but you see how that comes down and pretty much becomes flat along here. Okay, that's what you want to see. For efficient operation, we want to see this thing stay unloaded for 2 minutes on the average cycle. 2 minutes. 2 minutes is a long time. Got to have some big storage tanks to make that happen. But, you know, adding storage to a system is never hurts you. It's always a benefit, because the more air you have stored, the more potential energy you have to flatten out fluctuations. You know, you got a big use over here that opens up for 15 seconds. Well, if you don't have any storage, when that thing opens up, it's going to pull the pressure down on the whole system, and then the compressor is going to have to respond, and then the little man's going to have to do something. And so you're going to have all these pressure perturbations continually propagating through the system. And storage will mitigate a lot of that. Okay, now look at this one. What looks different about these traces? And that's a 450 horsepower Ingersoll Rand. Something screwy. I must have put the CT on upside down or something, right? It's not, no. So this was at Carlisle, pretty sure. Yeah, it says Carlisle. They make lawnmower tires for like Murray and all that stuff. Big plant. I think it was Jackson, Tennessee. We were there for a couple of days. Good size operation. And we had logged that. And the second day, the Ingersoll, we called, you know, we go to a visit, we like to call if there's compressed air people, you know, that actually work on the machines. We want them in, you know, we want to say, hey, what do you think? You know, you put your hands on this thing. You know, let's get together and work together and see what we can do to make this better. Well, so we were sitting there looking at that, and the Ingersoll Rand guy walked in, and I mean, he looked at that and he knew exactly. And I'm sitting there going, guys, man, I don't know. You know, usually it goes up, it doesn't go down. And the guy started laughing. He said, you've never seen that before, have you? And I said, no, sir. No, sir. I said, school me up. You got me on this one. He said, okay. So they have an option you can buy, at least they used to, I don't know if they still sell it, on their control package, that when this thing unloads, it looks at the rate of change of pressure And it tries to lengthen that cycle, keep it unloaded, keep it either loaded or unloaded longer to minimize the short cycling. So what they do is they use the modulation valve. So it's unloaded, and see the pressure's going up because it has to go up because it unloads. And if the pressure didn't go up, it would not unload. So the pressure's going up, but they're cracking back that modulation valve in order to slow the rate of pressure increase so they can keep the machine loaded longer and minimize the number of cycles. And they got some name for it. I don't know. I can't remember anymore the name of it. And so that's why the air production is going down, but it's not going down fast enough that the pressure stabilizes. The pressure keeps going up. So, I mean, I wish I had a pressure plot with that. You would see that pressure continue to go up, but the air production rate is going down after that thing loads, which is what causes the current to drop a little bit until it unloads. So anyway, I mean, you start logging these things and looking at them. Sometimes you see something that the compressor is malfunctioning. You know, sometimes it's just there's something wrong. You see all kinds of stuff. And that's why I just go notice the power falls as system pressure increase. Feature of some Ingersoll Rand compressors. Use modulation to extend the length of unload periods. I just got crazy about that. So, okay, here we go. So we'll spend a while on this. This is kind of where the rubber meets the road. These are a lot of the control curves for the screw compressors, okay? So I guess we'll go A, B, C, D. So A is modulation control. That's just that butterfly valve cranking back and forth. That's the solid curve all the way up here, okay? And so, you know, 100% capacity, if it's a 100 horse motor or 100 horse compressor, that's say 450 CFM. And that's probably, if it's a 100 horse motor, it's probably 110 horsepower at full load because they have designed into that service factor by 10%. They'll put a 15% service factor on the motor, which means it could pull 115 horsepower, and they will use 10 of those horsepower at full load. Very common. Because the first time you start taking measurements on these things, you start looking at that current and you go, well, that can't be right. It's a 100 horse motor. It shouldn't be able to pull that many amps. And then somebody says, they're in the service factor. And you go, what do you mean? So they design it for 110 horsepower. And they just hope the motor, they don't care if the motor burns up, that's your problem. You can buy an oversized motor, which is not a bad idea. If you're going to buy a 100 horse air compressor, buy a 125 horse motor on it. You have to pay more, but they'll sell it to you. They'll be happy to put that motor on there for you. Okay, so, you know, again, what's a good number here? 40% seems like it comes out even on a lot of these. 40%, we're still, what, 84% full load power at 40% airflow. What's your kW per 100 gonna do there? Maybe you're 18 kW per 100 over here, but what are you here? What are you at 40%? Not so good. We could calculate it. It's probably 25, 30, something like that, because that machine doesn't unload very well with modulation. So if you're operating a modulating machine, you darn well for efficiency, you want to keep it base loaded. So it doesn't hurt you if you've got 3 compressors, 2 of them are modulation and they're at 100% load all the time and you need the air, well, it doesn't hurt you a bit. That's good management. But if you've got 2 air compressors, one's a VFD, which is a good trim machine, one's a modulation machine, and you got the VFD at 100% and you got the modulation machine trimming the system, you shot yourself in the foot. You need to switch those. And now you go in these plants and sometimes they know, sometimes they don't know, and you get a guy switching compressors around, and you know, Lord knows what you're going to run into. Okay. This dotted line would be, some manufacturers set these things up. This thing can run modulation down to say 40%, and then it's going to run load unload from 40% down to 0%, because it's just so inefficient over here at 10, 15, 20%. Oh my gosh, it's just awful. Say, if you start running load unload, then your control curve becomes, on the low end, becomes this one, this dash line from here to here. And so if you were running 10% air with the auto dual controls going to load unload, you'd be 40% power at 10% air. Wow, that's a deal. Yeah. But if you're running straight modulation, you're what, 70, that's 75, you're 73%. So let's say you go in a plant and they just have one air compressor and they're running it at a lot of time at really low loads. Well, there may be an option in the controls that you can just hit a switch and change from this control mode to this control mode. So if they spend half their day at 10% air, you can save them, what is that, 73, 40, what's that, 33% of their compressor power by simply changing the control mode that may already be programmed into their controller that they don't know anything about. Interesting. Okay. So that's the modulation control. Then B is the active rotor length adjustment. So this, all these little triangles out here, these are different positions of the slider valve. Okay, so now we're no longer using that inlet valve. We have that slider valve that adjusts the point at which air is introduced into the screws. Okay, so as you change that valve position, you change the active rotor length, which changes the size of the compressor. So that's what we're doing, is we're making the compressor screws get bigger or smaller depending on the air demand. Okay, and so, well, you know what? That's not so bad compared to modulation. It's a pretty good deal, right? And so you see up in here, you know, if you're at 70%, if you were modulation, you'd be what, 92% power. If you're active rotor length, you're what, 77, 77 and a half. Well, that's better. That's an improvement. But see, it kind of trails off after you get down to like 40%, kind of diminishing returns. It's pretty good up here, and then it starts trailing off. When you get down to about 40%, that's it. They just can't, it doesn't work anymore. And so then they go load, unload. So you get from here to here, load, unload curve, and then above 40%, it switches to rotor length adjustment, and it comes up through here. Okay? Now, we've got the load, unload for curve C. Now, this is strictly, when you see this straight line, that's for a lube-free machine because it's a straight line. And so this compressor doesn't have the sump blowdown issue that we discussed because it doesn't have lubricant. So this machine, it's either running here or running here. And so you just draw a straight line, and if you're at 50% capacity, it spends half of its time here and half of its time here. And so on average, it's right here. Okay. Now, we'll continue the load unload discussion for the lube injected on another slide or two that's coming. But this strictly, when you see that straight line for load unload, it has to be lube free. Or you could say with tons of storage. If you can let it unloaded long enough every cycle, then you can get pretty much a straight curve. But most of them can't do that. Okay, and then we've got the VSD, the variable speed. So you see why everybody wants a variable speed machine for a trim machine. It's that much better. So we're just, that VFD, that little man is looking at his gauge, and now instead of having a toggle switch, he's got a crank. He's got a speed control. He's got a steering wheel in there. And so he's sitting there looking at that pressure to say, it's set, say he wants 100 pounds. It goes 101, 102, and he goes, no, 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 we got to slow down. So he turns the wheel this way. And then it drops back. And then it goes to 97, 96. You go, no, 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 we got to go this way. So he's just constantly sitting there, turning that speed control on that compressor up and down. So you can maintain, depending on the fluctuation in uses, you can maintain a pretty flat pressure. Yeah, question.
You said you see a straight, linear line, power input capacity, it's no lube?
Yeah, lube free. If it's a straight line, it's theoretically lube free, no lube. Or you could say if you had infinite storage, or a really lot of storage, you could approach that curve with a lube injected machine. Okay. But it wouldn't be that straight. If it's a 100% straight line, it's got to be a lube-free compressor. Okay, now you get down to the end, and this is kind of interesting. So these are Atlas Copco curves. Okay, and so they show bringing this thing down to, well, below, looks like about 18%. And then they just run load, unload. Then they turn it off. If the pressure goes up here, they just turn it off. But see, with the VFD, you can go to 0 because you can stop that motor any number of times you want to, because you don't stress the windings by starting across the line. See? So now Ingersoll Rand, golly, they cut theirs off, their VFDs off at like 40%. So an Ingersoll Rand curve, some of them I think even 50%. So if this was Ingersoll Rand curve, that dotted line would come in here and run all the way down. Now, Ingersoll Rand does that as much as anything for marketing purposes. And of course, think about it. Once you go to load, unload, you have to have a pressure band. You have to have a high pressure and a low pressure, right? Up until that point with a VFD, you just have one pressure set point. So you get much less pressure fluctuation. So once I get down in here, I'm going to have much more pressure fluctuation in my system because I have to have a band to operate off of, where I don't. Well, Ingersoll Rand is back here doing this load unload point from here on down. And they do it because they want to state the overall efficiency of their machine never goes above 20 kW per 100 for marketing purposes. What you're going to find, when you run these down at lower speeds, you lose efficiency. Because you've got your VFD loss, which is constant, and then at slower speeds, it's just not quite as efficient a process. Well, so your kW per 100 down in that low range will go 21, 22, 23. Ingersoll Rand says, no, we want to advertise our compressors as never going below 20 kW per 100. So they cut off the VFD at 40 to 50% and run load unload, which is more efficient than using the VFD at low load ranges. Now, I've been involved with the purchasing of compressor. We've had a couple of companies come back and ask us to review proposals or submittals. And yeah, I mean, it's fascinating to see, like Solaire and all that. Oh, they'll make a big deal about that. They'll say, oh, no, 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 that's going to cause more pressure fluctuation in your system, and it's going to be a terrible thing for you. And Ingersoll Rand said, oh, no, this is going to save you money. You see what I'm saying? I mean, they come at it from different angles, and then the companies butt heads and make different arguments that would lead you to their product. It's really pretty fascinating. Okay, I think that pretty well exhausts that. Okay, this is the Quincy poppet valves. They call this power sink, I think. And this is what the current traces look like. And so this is these poppet valves. It's like, here pressure went down in the system, and one of those, and then that last valve closed. And it say the current jumps from what, 115 to about 125, and that's when that valve closes and we get more capacity out of the machine, and then the pressure goes up, and then it get to the point that we're going to unload that valve. So we unload that valve and we drop down here to 115, 116, and then the pressure must be falling. I don't have a pressure trace on here, but the pressure must be falling, because then I load it back up again. I close that valve. And so those poppet valves are jumping back and forth. And here's a short time where we actually unloaded a second poppet valve. But boy, it didn't stay long. That second one popped, and the pressure must have plummeted, and it popped right back in, came up. So anyway. Quincy swears this is a very efficient way to adjust capacity on the machine. We've already talked about that. That's kind of redundant. And we've talked about that. Okay, so we'll do this and then we'll quit for today. Okay, so this is load unload for the lube injected compressor. Do any of those look like a dead straight line? And so the worst one is this one on top. This is called affectionately the banana curve, because it looks like a banana, at least the top part of it. And so this top one is 1 gallon per CFM of storage. So, you add up all the storage in your system, and that CFM refers to your trim compressor, the compressor that's loading and unloading with changes in air demand. So 1 gallon per CFM, and that's in the old days, like, I don't know, 30, 40 years ago, when everybody used the double acting recips, 1 gallon per CFM was adequate for those. But see, it's a different technology. And they don't have the sump. I mean, they just sit there, boom, 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 boom. They don't care, But so we've got this 40-second delay on the sump, which is the cause of all of this. So if I only have 1 gallon per CFM of storage, when that sump unloads, when that compressor unloads, it can only stay unloaded for 10 seconds, 15 seconds. It's short cycling because I don't have enough storage. And so that drives up my KW input because the current never falls, okay? And so I get this banana curve, the top. So, again, 40% works out well on these curves for some reason. So if I'm at 40% load, I'm about 81, 82% full load power. But look on the other side of it. What if I had 10 gallons per CFM of storage? Now, that could be a lot of, if it's 100 horse, let's say you have a 500 CFM compressor, 10 gallons, that's 5,000 gallons. Was it how many? 5,000 gallons, there's 7.48 gallons in a cubic foot. So 5,000 divided by 7.48. So that's like 670 cubic feet. And so let's just say 670. Say this thing was 6 foot square, that would be 36 divided by 36. So that thing would be 19 feet tall for a 100-horse air compressor. And, it would be round and all that, but, so 20 foot tall, that's a pretty big tank, So that's what 10 gallons per CFM would do. And so if you installed that in that system at 40%, you would drop to 60% power. So you would save 21 or 22% of your compressor energy based on these curves by buying that storage tank. And then you just got to figure out if that's where you operate all the time, you can go measure the power and see what that's worth to you and see what the payback is on that project. So we make this recommendation fairly frequently. Okay, and then the other lines are just different. I've got 1 gallon per CFM, 3, 5, and 10. So between 5 to 10 gallons, I mean, you'd really like to see 10, but and some plants have it. They really do. Okay, let's just see. So, well, this is the same thing. Okay, so we'll stop here and continue on next time. Hope everybody has a great day, rest of the day.